if you have a photon or beam of light and that you put through a polarizer in X direction. So if you put here a Polaroid in at angle theta to the beam, to the X-axis, and then you basically, and now you want to measure, and then here you have a Polaroid angle 0. Now you have basically shifted the polarization and you have put it into state X prime, which state X prime is basically state X adjusted by the angle of rotation theta. And then if you multiply this, if you multiply this by X, you get this, and then you can calculate this is cosinus theta. So the likelihood, so to know what is the likelihood of getting through this polarizer, you need to multiply by bra X, because this gives you the likelihood to go from this state into this state, right? And this is, if so, you have to multiply this by X and this by X and this by X, so you get cosinus theta X of X plus sinus theta F of X of X. But because the probability to go from X to X is of course 1, these terms go away, and from X to Y it's 0. So this becomes 0 times sinus theta. So this term is dropped. So you only have cosinus theta. And so now if you want the amplitude, this is the amplitude. Now if you want the probability, you have to square it. So then now the probability is cosinus squared theta. Now if you enter a value of theta, for example, the angle 30, and calculate it, then you get a probability of 75%. So now we have the chance of 75% that the photon will arrive here because as this angle was turned. And so this is how it works. It's really, you just have to use the equations, and if you now put in 100 photons, 75 will go through. And that's because and so it shows you that this law is really valid, and this. But you cannot tell at the level, and you can never tell at the level of a single photon which will go through. Okay, so I think we should start again. So this it seems quite horrible that I've chased away everybody, but I will close the door. Had a very good professor at college in Cologne. His name was Düsing. You may know him, Barry. Yeah. And he was a specialist in Aristotle and Kant, and he managed to really chase away everybody in his Kant Deduktion der reinen Verstandesbegriffe seminar. And so at the end, with just 3 students left, and he was delighted. He said, "Good morning, gentlemen. Oh, we have no ladies left. What a pity." And then he said, "Tres factum collegium." And then he started. So it was really. But today it's better. So we have a lady left. It's good. So let's go to continue. So basically, yeah, we were here. So this was this. I just to recap. This thing was the path. So here you have an oven producing particles, and they go through this 3 consecutive Stern-Gerlach apparatuses, and the first one is splitting them. The second one is basically just letting them go through, and the third one is reuniting them to one beam. And you can put in the second one, you can put blockers, right? And this where you can now, for example, if you have a spin 1 particle, you get 3 beams, and now you can block out beam 0 and beam -1, and then you get only beam plus. And now you can have different combinations of the filters, which are shown here in these symbols invented by Feynman. And now you can, and this is a key point, you can basically draw up a matrix of the likelihoods, how likely it is to go from one through the whole system if you put 2 filters next to the other. So we have a plus filter, and now of course the likelihood to go from plus S to plus S is 1. But if we have this filter, the likelihood to go from minus S to minus S is 0. And so if we combine the filters in this way and permute through all the filters, we can fill this matrix that shows that I have likelihoods to go from one state to the same state, always 1, but the other is always 0, which is a Kronecker delta. And if you do the rotation, then as we have seen, the likelihood is not anymore 1 to go from S plus to T plus, as we just showed. That's the photon experiment, basically. But it gets lower. And this is expressed in this equation here with the square, because the square, if you write it out, gives in a cosine term, which is added. And so this is how I just showed this. And so, but the probabilities to go from one state to the other state is always, you can always obtain it by expressing this state's likelihood to go into a base state, like base state 1, and then from base state 1 to this state. If you sum them, then you get this amplitude. And so this is basically what I wanted to recap. Now, what is a quantum bit? So these were the two states, 0 and 1, or 1 and 2 of ammonium. I think this is state 1 is here on the left and state 2 is on the right. I just cut off the 2, which was in the original picture. And these are the two base states, and now we saw that we can describe any state as combination of these two base states if we abstract from everything else, right? All the other states in which the ammonium molecule can be, if we just concentrate on the nitrogen being up or down as the two base states.
So the states are always geometric.
Yeah, the states are always chosen as to be the basis of the Hilbert space. Right?
Geometric. So what defines up and down?
So geometric, that's a good question. So geometric means that basically you now call the Hilbert space geometric. Hilbert would be delighted, because his first book, when he was a young mathematician, I read it when I was 16 or 17, was Grundlagen der Geometrie. So he started with geometry, and then he developed k-dimensional geometry, right? And so that's how he ended up with the Hilbert space. So he would really be delighted about your remark. So that means that you just have a coordinate system. There's a Hilbert space, a coordinate system, and then you add more and more axes. But this one has just 2 axes, this coordinate system, and it does not. But it's a coordinate system that has axes, but it also has a metric, which is the inner product. And the inner product is this. This is just the inner product of the Hilbert space. The bracket.
Yeah.
Like this is phi psi, the likelihood to go from psi to phi, or to go from state phi from state psi to state phi. This is the inner product of the space, and you can also write it out as an integral, but we are not doing this here because it's too mathematically complicated. Therefore, I am only showing, and this is a discrete Hilbert space, right? In discrete Hilbert space, and all the quantum computers are discrete Hilbert space. You can always do sums instead of integrals, and just sum over the. So here you have now the sum of this energy level multiplied by C1 plus by C2, and this gives you the likelihood of going from this is the likelihood. Where did I write this down? Yes, this is the likelihood to go from C into state C1, right? So this is the likelihood of going from a state C into state 1, and this is just, or this is the function of this likelihood, and this is how it is obtained in discrete discrete Hilbert space. And now and so the directions in this case are orthogonal. So that was your questions. How are the spin up and spin down defined? They are defined by 2 orthogonal vectors. So it's not like being negative on one x. So it's not that you say, change, I have here a line and now here's 0. And if I'm here, I'm stay up and spin down. That's wrong. But it's like this. So this is one state and this is the other state, right? And then the third state would also get, would be here, would be like this, orthogonal to the other one. That would then state 3, and if you put them in a matrix, 1, 2, 3, 1, 2, 3, then you get this Kronecker matrix, which tells you that I have a likelihood of 1 to go from one state to the other state. And then I can say, I have a state C, and this is now the sum of C1, the complex number, by each state, each basis state multiplied by this complex number. And this is what we had in the last lecture. And here again, you see you have this state C, which is a sum of a projector into the first step, the projector into the first, not just a number, but it's a projector into the first state, and that's a projector into the second state. You see that the C is multiplied by this projector, and this is the same as basically saying I multiply the state 1 cat by C1 and C2, which is the probability again of C going into the state. And so this is now, and this is again shows you this relationship. So here you have one state, for example, that's a Z plus state that is spin up in the Z direction, and orthogonal to it you have spin down in the Z direction. And now you could have here he's showing X, which is yet another orthogonal, but it gets hard to show here, because of course in 2 dimensions you can't show it anymore properly. But basically that's now the spin up in the X direction. And so then you can add more and more states. And if you do this and do so Schrödinger equation, you really compute everything, then you can only do the helium atom. Because afterwards the coordinate system gets so complicated that there is no numerical solution anymore. So you cannot solve the integrals by hand anymore, but also it becomes computationally super hard to find solutions, even with today's computers. Because there are so many parameters then going into this that the equations become very, very hard to solve. I mean, they're differential equations. These are partial differential equations. And so you saw yourself in our book that we can only solve equations with 4 or 5 variables. And if we have many more, it gets very, very hard and computationally very expensive. And so that's the limitation of quantum mechanics. That in theory, it's a great equation, but it only applies to very few particles.
Now we have ChatGPT.
Is this the kind of mathematical problem that precisely quantum computers could help us solve because of their processing power?
So in 1981, so the whole myth of the processing power, I think we destroyed today. But there are several basic ways to use a quantum computer. One is what you were alluding to, is the processing power, which only exists for certain selected problems, but which you will I hope at the end of this morning you will see this. Then we have the idea that Feynman brought forward in 1981, which was to use when he was in his 60s, and that was his idea, late 50s, and no, he was in his 60s, I think. That was the idea to use the quantum computer to simulate natural quantum systems. So to build, so like in analog computing, to basically have a computer that works really like what is happening in nature, and so that you can basically directly model quantum interactions natively. We are not going to discuss this today, but if such computers can ever be built, they will certainly be able to model they could be able to model atoms at the quantum level that are more complicated than helium, but I doubt that they can model, really complex interactions. And if you look at what's being today done in molecular interactions, mostly based on thermodynamics and the Hamiltonian they use, which is this matrix for the energy levels, right? This matrix, they use a Hamiltonian, but they use a Newtonian Hamiltonian, not a quantum Hamiltonian, because the particles, they're looking at the particles at the 2 are already at an aggregate level, so they are not looking at 1 or 2 particles anymore, but they look at a lot of, if you have a protein surface, there are many atoms contributing to the surface shape, and then the ligand contains also maybe a small ligand contains already atoms, maybe like aspirin, and then so many entities interact, and they are quite big from a quantum perspective, that now you have again a classical Newtonian problem. And so what they do is that they have a Hamiltonian, but that they use it in the Hamiltonian, in the Newtonian sense. So and I don't see that this will be overcome anytime soon. Now going back to the quantum bit, quantum bit is really such a space with, oh yes,
Concerning the process of computers, I was reading yesterday, and it says that one of the biggest problems is that they are more unstable, and therefore the channel are more noisy. The information.
yeah, we get to this. So this comes later in today's lecture. This is of course a very big problem. So let's go look at the quantum bit once more. The quantum bit is always using a very simple basis of 0 and 1 state, and which are written like these vectors. Here you see again the sphere. You have, this is very important. You have now one qubit, which might be an atom that is now in a higher excitation state and lower excitation state, and so psi means, of course, that it's between these two states, and there are infinitely many possibilities to be between these two states of excitation. And the pure state is defined by the quantum energy of an electron, and therefore, you know, when you have, for example, an electron falling down from a higher energy level to a lower energy level, then a certain quantum of light is emitted very. That's what Planck discovered, that this quantum of light is always the same. But of course, when the atom can of course be in states in between, and the sphere indicates, if you move this point on the sphere, you have infinitely many positions, and these positions are all linear combinations of the state 0 and state 1, and they can be expressed according to the Euler formula. They can be, because of this, they can be expressed with cosinus theta half plus cosine theta half plus sine theta half multiplied by e exponent I. And so this just tells you that how you calculate the position given the angles on the sphere, right? So you have infinitely many angles, phi and theta, and now if you plug them into this equation, then it will just give out the value of the state base as expressed in the basis of the two states. That's really linear algebra, basically. And so this is just to show you that there are infinitely many qubits.
Okay, now before you move on, you at the bottom of this screen you have quantum computers manipulate continuous magnitudes, quantum mechanical waves in infinite Hilbert space.
Yes.
Now, quantum computers are technological devices. That they are devices which can be understood also from the perspective of ordinary common sense. So, what is the sphere in this?
In the sphere, when the qubit gets manipulated, so you start. So let's start with the quantum register. The quantum register is a set of qubits. For example, 2 or 8 qubits,
Which are
which each of them you can imagine as a sphere, right? And so when you put them together in a quantum circuit, so to speak, then if you put them together, then the spheres combine to a big Hilbert space that you cannot imagine anymore draw. So the Hilbert sphere is only to help you understand one single qubit. The Bloch sphere.
Yeah.
The Bloch sphere is only, and that was not Ernst Bloch, I can assure you, the philosopher, the Marxist philosopher. So when you get this, then you get this tensor product, which I explained here. So even if you just put two vectors together, you already get, now if you put these together, it gets, the matrix gets bigger and bigger. And this matrix, this huge matrix, is then the tensor product of all the basic qubits. And that is dimensionality is C, D is 2 times n. So then you have, if you have 8, you have 2 to the 16 dimensions of this matrix. And so then you have basically, when you switch this computer on, and you want to start the whole register or with all the states set to 0, right? And already this you don't achieve because in reality you can't set them to 0. You can only set them approximately to 0. And then what you have is that you have a quantum wave, a wave function describing the physical state of these 8 resonances as one system. There are now one system. And this is a high dimensional wave that is there that depends on the state of each of the bits of the register. And now manipulating is means you apply energy to one of them, and this way you change one of the qubits. And by doing this, or several, and by doing this, you change the shape of the wave.
Okay, so you have
That's manipulating a qubit.
you have the entire registry, which has a huge number of
Hilbert space dimension.
dimensions,
Even if it has only 8 qubits.
and you have single qubits, which you can somehow give energy to.
Yes, with a laser. You just shoot on the qubit with a laser,
Okay, but where?
for example.
How so it's spatial. Somewhere it's somewhere.
So it's the ion track. So there's a small chamber.
Yeah.
In this chamber, you have a magnetic force or electromagnetic force which holds an ion in calcium, potassium or calcium ion in suspension. Now you freeze it to 0.1 Kelvin, and therefore you hope that it gets into state 0. Now there's a small laser, and you shoot a bit of laser light over it, and it will get into state 1.
Okay, now how does that ion in that chamber relate to this gigantic register?
Oh, because there are 8 ions. So you should have 8 qubits. They're just 8 ions aligned in one row.
Okay.
And with 8 laser beams,
Okay. So the qubit is really an ion.
it can be, yeah, or the photon. I mean, whatever, you can also
Okay, I get it.
it's a physical entity.
But you manipulate, is the idea that you manipulate only one of the qubits, like one of these particles, and then because they are interlinked in the registry, that
Yeah, so I don't.
connection between them?
Yeah, you can. So when you manipulate one of them, you manipulate the entire wave, but you can also manipulate several at a time, depending on the quantum operator that you're applying, right? So you have different quantum operators, and the quantum operator, mathematically, the quantum operator or projector, which is this what we had last time, which we are now going to repeat. This basically is a mathematical description of what you should do with the lasers to manipulate the state of the ion. And then if you apply this energy, you get a change of the wave function, and this is your computation, right? And so but before that, so here's a register of 2 qubits. It has the basis 00, 01, 10, and 11. And now the wave that is happening, the wave that is, so to speak, occurring in this space is basically the sum of those different basis states multiplied by a complex number plus the next base state, the next base. So you have, that's a sum of 4. C1 multiplied by 00 plus C2 multiplied by 01 plus C3 multiplied by 10 plus C4 multiplied by 11. And this together describes now the state, the register state, which is not anymore the Barry, if you look at this equation, that's the register state, not anymore the qubit state. And because there's a complex number written there, you have, of course, infinitely many possibilities of how this state, capital uppercase psi, can look like. And now, so this is again the key. We discussed entanglement yesterday, photon entanglement. This is also a type of entanglement of 2 basis qubit states. And so we have now 2 qubits which are entangled, and they cannot be factored into a product of the states of the first and second bit because it's a sum, right? So we cannot write down them as a product. Therefore, this is not interpretable, as Griffiths would say. I explained this yesterday. That because I cannot, the projector is not how does it call it? It doesn't commute, because the projector doesn't commute to achieve this entangled state, so it's a non-interpretable state. But this is the key why quantum computers have the higher efficacy than normal computers, because you can now create entangled states. And in an entangled state, this goes back to your question, but if you manage to entangle all your 8 qubits of your register, then you only have to manipulate 1 qubit to manipulate them all. because manipulating one. So if you think of the entangled photons example, they are now far apart. Alice has one, Bob has one. If Bob measures his qubit, Alice doesn't have to measure her qubit anymore because she knows that it has the opposite spin, right? Or the same spin if the entanglement is positive. And so this entanglement is the reason. So what you do in quantum computer is you create entanglement spaces, entanglements, then you manipulate only one qubit, and by doing this, then you manipulate all the other qubits as well.
But you manipulate one qubit, thereby change the entire wave.
Yes.
But how do you direct the manipulation so that it changes the entire wave?
This we will see now.
Direction that is useful.
This we will see now. So this you do because in quantum mechanics, every manipulation of a quantum state is a multiplication with an operator. And so this is just, I haven't shown this so well. Well, I showed it a bit in the measurement case, because here the measurement case, as you see, if you make a measurement, you basically multiply the to see the probability of being in state 0. You take a measurement that measures spin down, for example, x direction, multiply this by the ket, and then by the bra. And by this, you basically, if you leave the m out here, you have always 1, because you like to go from side to side. But if you put this into the middle, then you get a measurement of the likelihood of being and if you square this, then you get the measurement, you get the likelihood of being in. Here you can nicely see, by the way, why the square of the amplitude is a probability, right? Because basically you have the state here twice, and so in quantum mechanics, any change of a quantum system is always a multiplication with a matrix, and in quantum computing it's a unitary matrix, which is a quadratic matrix. And so I put yesterday on the whiteboard what happens when you multiply the state, and I will do this again because I complained a bit about the mathematics to do it more slowly.
Use a really good black. Yeah.
So if we have, I show here that this should be clear to you. So alpha, so 0, so your vector 0 is 1, 0. So if you multiply 1, so I do this very slowly. And so if I add these two together, then I get alpha beta. Because vector addition is just this plus this goes in the third, and this plus this goes there. So this is basically explains you why adding these two yields alpha beta as vector. And so you see now these are the complex numbers with which I have to multiply the state, right? And if I multiply 0, and so therefore now my vector is not anymore the combination of 1 and 0, but it's now alpha beta. These are now the values of the complex numbers with which I have to multiply the two states. And now, if I multiply this, which is now my psi, what is it here, psi? If I multiply psi by u, I have u is 0, 1, 1, 0, and psi is alpha beta. And this is really a nice example, because what we see now is, so how to determine the new positions. So I have to do 0 times alpha. Sorry, this is correct. Yes. 0 times alpha plus 1 times beta gives beta, and 1 times alpha plus 0 times beta gives alpha. So this is just 0 times alpha plus 1 times beta, so rho by beta column. 0, that's a rule for multiplication. Rho times column. 0 times alpha plus 1 times beta is beta. 1 times alpha plus 0 times beta is alpha. Right? And so, or I could again get full 0 times alpha plus 1 times beta, and this is 0 times beta plus 1 times alpha. And everything in quantum computing works like this. You only have to stupidly apply the rules of matrix multiplication, which is the first position is filled by doing row times column, the second position is second row times column. This way, this is just very, this is what Gauss invented, right? This is simple linear algebra matrix multiplication. I think we even had this at school, all of us. Only later it can become more complicated, but this we all had at school. And so this is what you get. So what does this operate, this matrix U do? It inverts the order of the bits. And so that's really happening now. So now these two are swapped.
So go back to the ion and the gun that you shoot it with. Shooting the ion changes the order of the bits across the entire way.
But this is 1 qubit, right? Only. So
I think this is only one.
this is only 1 qubit. So now we have only manipulated 1 qubit.
And if you have 8 qubits, you have 8 guns.
I have not, to be honest, looked so much into the details of the realization of the operators.
Okay, that's the second part.
No, it's a completely boring part, and it's different for any implementation of a quantum computer. There are many, I've seen you. There are many different ways to implement them. I'm not a quantum computer engineer, so I haven't looked into which is currently the one that they're doing. I think the one they're doing is with the Josephson junction, which is a very strong magnetic field where you use a quantum effect of an electron bridge. It's also built. Yes, but yes, and it's also a quantum sensor. And I think what they now do, they don't shoot with a laser, but they manipulate these Josephson junctions by putting more or less electricity on them. But I don't know which operator is realized with which manipulation device in which quantum computer. I mean, this is very trivial. But if you have understood, so why I'm only talking about the matrices is because I think this is what you need to understand first, and it would take a lot of time and showing engineering diagrams to show how this is then realized. I've quickly looked at some, but I decided that it's not interesting for this lecture. But the principle is that you can build physical devices that realize each of this operator in a physical way, right? So now your question.
Right. So just to get it, so that I'm getting it wrong. The psycad, it's the state, it represents the state of the qubit.
Of the 1 qubit, yes, one.
1 qubit, yes. And then the U operator, this is the manipulation that you compose on it. So really the logical operation is done in the manipulation of the qubit.
Yes. And so the quantum gate, this is a quantum gate. And we had the logic gates yesterday. The logic gates are transistors chained together in a clever way. This here is really an energy level change in the energy level of the quantum register, which is applied, for example, by laser, or the other one would be to change the electric field in the Josephson junction. That is a squid, right? But for each of the operators, there is a physical realization of it in a certain type of quantum computer. Okay, now we have the most important operator that exists is the C0 gate, which is a controlled NOT gate. Simple quantum gate is a C0. It only negates the second qubit and leaves the first unchanged. So for this, we already need a 4 times 4 matrix, which we apply to 2 bits. And 2 bits, of course, they are already 4 by 4 vector. But 2 bits like this 0, 0 bit is, of course, 1, 0, 1, 0, and the 0, 1 bit is 1, 0, 0, 1, and the 1, 1 bit is 0, 1, 0, 1, and so on. Yeah, so the 2-bit register is represented by 4. I have it here. Okay. Okay, they have actually a different nomenclature. So these are wrong because I use a different nomenclature. But this is the nomenclature that they use here to represent these 4 bits for tuples. I see what they did. Okay. So they use basically, what I did, I combined the 1-bit 0 with the 1-bit 1, but they have now changed the nomenclature to just make it use less ones, but it's equivalent to what I wrote down. So basically here this indicates the first set, second set, and fourth set. It's simpler than what now you can multiply this, of course, with the C0 gate. And so the C0 gate works like this. The first input just stays the same in the C0 gate, and the second input will be subjected to a XOR. This means XOR, exclusive OR. And so it is an addition with division modulo 2. So let me show you what that means. So if I have here A and B and then XOR, we have looked at it yesterday. I can have 0, 0, 1, 1 here, and then 0, 1, 0, 1 here. I think this gives me all 4 combinations. So in an exclusive OR gate, this is the result. Now, what does this plus do? This plus creates 0 modulo 2, 0 plus 1 is 1 modulo 2, 1 plus 0 is 1 modulo 2, and 1 plus 1 is 2 modulo 2. 2 modulo 2 means how often can what is the rest after dividing 2 by 2? The rest after dividing 2 by 2 is 0. The rest after dividing 0 by 2 is 2, because 0 fits 0 times into 2. So I have 2, it's also 0 modulo 2 is also 0, because I get a 0 out of it. But if I divide 1 by 2, I can't do this, so I have 2 left. And the same is here. So this plus sign, which is addition mod 2, just gives me the same effect. It's the same so the XOR is the same than this encircled plus. And so now if we look at this and we apply this XOR gate to this 2-bit quantum register, we get for 0, 0, we get 0, 0, because the first bit is not altered. So if you look at the first column here, it's the same as the first column here, but the second column is different because this is just applying the exclusive OR. So now the second column is obtained by looking, I have 0 or a 1. Yes, that's true. So this becomes 1. Here I have a 1 or a 0. So this becomes 1. But the exclusive OR doesn't allow 2 1s to become a 1. So this becomes a 0. And so so basically, more generally speaking, the C0 gate transforms the quantum state shown here into this quantum state. So this stays the same. This becomes 0. This becomes 1. This stays 1. And so why is this so important? Because when you combine C0 gates, you can get higher operations. So it's even stronger. There's a second operator, which is called Hadamard, the Hadamard gate. So we have the C0 gate and the Hadamard gate. And if you, or Hadamard, and if you use, I think it was Frenchman, if you use C0 and Hadamard together and combine them cleverly, you can obtain any quantum circuit. So any quantum circuit, I think the exclusive OR and the AND gate, or 2 of the classical logic gates can also combine to create any logical circuit in a classical computer. And in the same way, you can obtain any quantum circuit by combining the Hadamard and the C0 gate. That's why they are so important. That's why I'm introducing them. And remember, these gates are multipliers. So these results that I showed here are obtained if I take this matrix and multiply it by this and do, what I just did, row 1 times column to fill the first, then row 2 times. Shall we do it for once for the big matrix or rather not? Do you want to see it as an exercise, or do you? It's the same that I did here, right? Just with more numbers.
I would like to hear more about the Hadamard gate.
We'll come to the Hadamard gate. So the Hadamard gate is this. So it performs a q-bit rotation. So if you have the base, so the base state 0 is mapped to 0 plus 1, and 1 is mapped to 0 minus 1 divided by square root of 2. So what does this do? It creates an entanglement. So wow, this is an entanglement gate. And this is the key thing. I just said at the beginning that by doing entanglement, that is the mystery of the quantum computer, is that just I create entanglements, and then I can perform all my calculations on the entangled states. And I need only to manipulate one single qubit to manipulate the whole gate, the whole quantum register. And so here you can see how the Hadamard gate is mapping basic states to entanglement states. And that's entanglement superposition. And the Hadamard gate performs basically, geometrically speaking, to use this nice phrase use again, on the Bloch sphere of one qubit, it performs a rotation of pi about the axis x plus z divided by square root of 2. And this is the Hadamard matrix. It's 1 divided by square root of 2 times this matrix. And so now we are going to, where's an eraser here? Now we're going to multiply one qubit with the Hadamard matrix so that you see what's going on. So the Hadamard matrix is 1, yeah. Now this is qubit 1, sorry, qubit 0. And so what's going on now? We have to multiply the row 1 by the column 1. So that gives us 1. This gives us 1 times 1 is 1, plus 1 times 1 is 2. And then it gives us sorry, I need to, yeah, that's right. And then 1 times 0, 1 times 1 is 1, plus minus 1 times 0 is 0. So this gives us 1. And so this gives us, how does this work? Sorry, I need to.
Surely it's 1 at the top.
Yeah, no, sorry, it's, yes, of course, it's 1 at the top. It's 1 times 1 plus 1 times 0, thank you, Barry, and that's minus 1 times 1 plus 0, that's minus 1. So this gives us, this gives us this. Right, so this gives us this. 1 minus 1, and the other one gives us, if we...
No, I think it's 1 at the bottom.
No, it's minus 1 times 1 plus 0 is minus 1.
No, it's 1 times 1 plus minus.
Ah, yeah, sorry. This one as well. So this is, you're right. And now let's do the other one with 1, 0, and this should give the opposite. So if you have the Hadamard gate here, you're right. This just gives the opposite. So now we have 1 times 0 plus 1 times 1 is 1. And then we have 1 times 0 plus minus 1 times 1 is minus 1. So this is this cat, and this is this cat. And so you see here that we now get this vector with the inverse sign. And so we get here then the minus here and the plus there. And that's what it does. That's how it does its rotation. And so now if we apply, so this was applying it to 1 qubit, but if we apply it to 2 qubits, so if you apply Hadamard matrix to 2 qubit register, then you obtain the entanglement that we see here on the board, 1/2 times 1 plus state 1 plus 1 tensor state 0 plus 1, and that equals 0 0 plus 0 1 plus 1 0 plus 1 1. And that's the state that cannot be factored into a product of the state of the base states. Now, if we now do a Hadamard rotation first, and then the C0 gate acts differently on the Hadamard based register than on the non-rotated base states 0 1. So here I have now put my 2 bits, which were originally 0 1, into a Hadamard state, which is this state in the computational basis 1 half 0 0 plus 0 1 plus 1 0 plus 1 1. Here's the second one, which is this, and the third one is in the 4 and now. Now I apply the C naught, and so so then I obtain this result, plus plus minus 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 plus plus minus. Whereas if I apply it to the non-rotated base, I receive 0 0 0 1 1 1 1 0. This is the not effect on the non-rotated basis, and this is on the rotated basis. And so you see that now I get a different output. And so what that means is basically that the computational basis 0 1 is the eigenbasis for the quantum magnitude in the z direction, and the Hadamard is the eigenbasis for the magnitude in the x direction. And so you see this here on the Hadamard sphere again, so that if you have a rotation by pi to get from the z to the y axis to the x axis, and this is basically what it does. So I get from one orientation to another orientation of the base states. Now, like in logical computers, a quantum circuit is made of quantum gates which are applied to a quantum register. So now I'm combining many quantum gates to get a circuit. And that's the same in logical computers. I'm combining many logical gates to get a circuit, like the adder we saw yesterday. Now I'm combining the gates, and by doing this, I apply those gates to a quantum register in an ordered manner. And so mathematically speaking, the quantum circuit is a unitary transformation using a matrix, which is a product of the matrix of the individual quantum gates. So I can, for example, make a product of the U gate that switches the order of the bits and the Hadamard gate that rotates them to get them into the entanglement state. And if I can now multiply these two matrices, and then if I apply them to the original state, I get my computation. And so Deutsch conceived in 1985, he conceived the first quantum circuit theoretically with his Deutsch algorithm. We will look at it now, and it was the first quantum algorithm to be realized. It was used on a single qubit calcium ion trap with 1 degree of freedom. That was manipulated with a laser. And so this is the circuit scheme of the Deutsch algorithm. So these are the two states of the bit. And now we apply Hadamard transformation to it, and then we apply the Deutsch function, and then we do on the first we do a measurement. And this is a very simple circuit, right? It has only Hadamard, and then this function here that we will look at in a minute. And the Deutsch algorithm determines whether a function operating on one qubit is constant or balanced. So if you have the qubit with 0 and 1, now the function maps from 0 1 to 0 1. Or from 0 1 to 1 0. Right? And so if it does this, so if it takes a 0 and always creates a 0, or if it takes a 1 and always creates a 1, it's like a coin with only one side. So where you have the head on the two sides, no matter whether you throw it, you always obtain the same side. If the function inverts, it's like a real coin, because you have a chance, if you put in a 0, you have a chance of 1/2 to get a 1 and vice versa. And so this is of course a completely useless example, right? He invented it because it was the only one that worked on one single qubit. But it was the first quantum algorithm which solved the problem faster than a classical computer, because in the classical computer you need to look at both sides of the coin. So you need two measurements. And here you only need one measurement, because you measure the entangled state. So the task is to find whether f is constant, so f of 0 is 1, or balanced f of 0 is is not 1. F is only given as a black box, and we can only observe which output f of b is computed for a given bit b. The classical solution would require to compute f0 and f1 and to compare the results. So we would compute f0, and if we get then f0 and then we do f1 and get f1, we know that's unfair. If you compute f1 and get f0 and then f1 and get 1, then it's fair. The Deutsch algorithm only needs one computation. The quantum algorithm applies the function to a superposition of the base states, and a clever evaluation of the results provides the required information about both outcomes of the function. This is the key, ladies and gentlemen, how quantum computing works, that you basically set up a circuit that allows you to find something with less measurements than you would have to do with a classical computer. And that was the idea of Deutsch. And so now I mentioned yesterday that quantum computing must always be reversible, right? And so the Deutsch algorithm works like a XOR gate, and XOR gate to make it reversible. And so you see here, I wrote this down already in this table, but you see it again. If I add 0 and 0 and divide this by 2, I get as a rest result 0. Yeah, because 0 divided by 2 is 0, so I have no rest. If I add 1 and 1 and divide it by 2, then I also have rest 0. Because 2 fits exactly 1 times into 2. If I divide 5 by 2, modulo 2 is 1, because 5 divided by 2 is 4 divided by 2 plus 1. And so then I get 1. But here, if I divide 1 by 2, I have 1 as well. And so this is how modulo works. And now Deutsch algorithm has used a register. Oh, sorry, it has 2 qubits. Of course, it's 2 qubits, not 2 qubits. And it consists of the following steps. So first, you initialize the qubits to have the first in state 1, the second in state, the first in state 0, and the second in state 1. Then you apply a Hadamard transform, which they call state A now, the combined state of the 2 qubits. So that's the state of each of the qubits, and the A is a register state. Now you take the 2 qubits and apply the Hadamard transformation to them, which gives you 1/2 0 plus 1 times, because they are together in one register. You use the tensor product. And so this is this tensor product 1/2 0 minus 1. We saw it here, right? That this is 0 plus 1 tensor product 0 minus or 0 minus 1. If in this so in this case you have 0 minus 1 plus 1 0 minus 1 1. And this is what it does here. It computes the base state, and so now you have this 0 0 minus 0 1 plus 1 0 minus 1 1. Now you have this Hadamard state now applied to the 2 qubit register, which they now call B as a summary. So this is now, of course, an entanglement state, right? Now you evaluate the function UF. So now, Barry, you will upload this, right? Anyhow.
Yes.
So now you want to evaluate UF. And so we don't have to go through the entire, so this is now, remember, we have this register state now. Yeah, so we do 2 Hadamard, and if you look at the circuit, you see it here. This is the first Hadamard transform, that's the second Hadamard transform. Oh, and this is basically already for the Deutsch-Josa algorithm. So you can ignore the cross n, it's just the h, and here it's just h. This is just already the circuit for n qubits, but we are only looking at 2 qubits. So Hadamard is applied twice, as you see here, to each of the qubits. Then we get this product, and now we take this and apply f. So first we apply f to this bit, and you know that the function, the XOR function, leaves the first bit unchanged. So this stays this, and the first we have to apply 0 modulo f of 0. So that's XOR, right? So XOR gate, as you saw here, applied to we can go back to this so that you understand this. So if you C not gate, if you apply the C not gate, the first bit is unchanged, and the second bit, so this is unchanged, and the second bit gets an XOR, and that's what's happening here. So the first bit is always unchanged. So that's the input. First bit unchanged, first bit unchanged, first bit unchanged, first bit unchanged. Second bit is always applied to the function. The function does just an XOR on the second bit. So it takes the second bit, which is O, and says plus f of O. And then this is done for every of the 4 combinations of the entangled state. Now, here's by simple algebra, the cat 0 is taken out of the product so that you have only f of O minus 1 plus f of 0, which comes from here. And here the plus 1 bit, which comes from here, and here is taken out and factored out, and you have f of 1 minus 1 plus f of 1. Now, you can put f of 1, f of 0 gives always 0 or 1. So you can put it into the exponent and factor out the minus sign. And then you get this. And then you, by simple transformation, you get this, and this all together gives you the state C. And now it's the interesting thing. If f of 0 is 0, then this term drops, and this term creates gives you this, right? And because this is basically plus minus 0, so the minus can be put back in here, and then you get 0 plus 1. And the other one, sorry, that's the 0 plus 1 comes from here, and the 0 minus 1 comes from here. And if C is not constant, then the F0 will be 1, and F1 will be 0, and then the result is this. So now you have 2 bits, right? The first bit is this bit, and the second bit is this bit. And now you take this first bit and apply, which has either plus sign if the coin is unfair. So if it's constant, if f of 0 is 0, and if it's fair, you get a minus sign here. The second bit is the same. And now you apply the Hadamard transform to the first qubit, and then you measure it. And if it has value 0, then f is constant, and if it doesn't have value 0, then it is balanced. And so that means that the whole trick of the Deutsch algorithm is to put all the information that is required to understand into the first bit. And so then you only need to so the operators have an effect on reordering the states of the bit so that you can distinguish them by this sign. And this is what is just being done. And I think that this is how every algorithm in quantum mechanics works. And so you can also generalize this to n input bits. Then that's called the Deutsch-Jose algorithm, which was published a bit later. And this is very interesting because this is what Turkwood shows. It shows what happens with n bits. Then the algorithm becomes more complicated. But basically, if you have n inputs bits, the Deutsch-Jose algorithm needs only one evaluation of the function f compared to a classical computer, which needs 2 exponent n divided by 3 computations. So if you have, for example, 8 bits, that's 21 evaluations. No, sorry, 8 bits. That's 256 divided by 3. That's more than 80 more than 80 computations with the classical algorithm and 1 with the Deutsch-Jose algorithm. And if you have 100 bits or so, then it becomes really better. So this is how it works. So the trick is really to apply transformations to the entanglement state that allow you to recover all the information from the first bit. And this is how it works. And it looks very impressive. I mean, the Deutsch algorithm itself is not so impressive because instead of 2 measurements you get 1, but that's only because we have just a 2-qubit system. But if you apply it to many coins that get flipped, that becomes very, very efficient. It's very impressive, but it has no applications. It's completely practically irrelevant. The comparison is unfair because the quantum evaluation is much harder to realize than a classical computation. So to build this circuit in a logical computer is very cheap, right? You can program it into a pocket calculator. But to build this algorithm into a so I had a pocket calculator in 1980 where I learned programming in Fortran, where I didn't implement this algorithm because that was even before quantum computers were invented. But I programmed, for example, n-faculty into it, right? And so n-faculty is a more complicated algorithm than this one. So already these old pocket computers could calculate this. And so so the comparison is not really fair. That's point number 2. And also, if you take a classic computer and put in a random generator, then you actually do the following. You compute F several times, get the results, and estimate whether the coin, probabilistically, whether the coin is correct. And then you, if you have now a number of n like 10 or n like 20, then maybe the Hadamard, the Deutsch user algorithm will take 1 measurement, but you will have maybe 5 measurements or 4, because with these 4 or 5 measurements, you can already extrapolate with a very good likelihood the nature of the function. Nevertheless, the algorithm is the smallest example of the advantage of quantum computing and shows how entanglement is utilized for speed up. So it really shows you, I create with the Hadamard gets entangled state. I have a gate that manipulates these entangled states so that I only need to measure 1 qubit. And with the Deutsch user algorithm, which I won't show because it takes too long, you even can do this with infinitely many qubits, right? And still concentrate all the information in the first qubit. This is very impressive. And this shows you the power of entanglement. Any questions? Before I get to your question about the physical problems.
But you said that it's nice, but it's not super practical algorithm. What do you mean by this?
It has no practice. There is no problem in reality to which you can apply the algorithm. So there are other quantum algorithms which can use to do real computations to solve real problems that are really painful, like encryption. So there's a quantum algorithm that you can use for encryption that is of practical use. But in the end, you know, the whole purpose of quantum computing theory is to build real quantum computers that have real use in real life. I mean, computer theory, also even for classical computers, if you wouldn't build computers, it would be a very, very sterile and useless part of mathematics because it's not even very beautiful. And so from a mathematical perspective, the quantum computer theory is very unsatisfying. We don't know much about complexity classes and which problems are amenable to quantum computing and so on, because we don't understand the quantum world really well. And so we use our partial knowledge of the quantum world to design computers, but mathematically you don't understand them. And so if you read papers about the theory of quantum computers, they are full of open questions. It's really ugly, mathematically speaking. And that's because we have so little knowledge. So that said, so therefore, all of this rather ugly science can only be, you know, kind of taken into account and conducted if you have a real practical use for it, right? And so this algorithm is just there to show how, in theory, a quantum computer can beat a classical computer, but it's not doing anything useful.
So, but are there quantum computers, which today are already doing something useful in the area of cryptography?
No. And the reason is that to do that, you need 1,000 qubits, but the biggest computer we have now has between 50 and 100. So sometimes the Japanese publish papers.
I think IBM is now up to like almost 400.
Yes, but that's a different type of computer. That is only a computer that can only do the haystack search. So it's not a flexible algorithm. It's a very special type of quantum computer application that can only do search for one data point in a huge set of data points. That has 400 qubits, but there is no quantum computer that can do, for example, number factorization, which is one of the cryptography, prime number factorization of numbers, is super important application. And this one has no quantum computer yet. And the one with the 400 is very specialized. But I have to admit that I haven't looked at it very much, what it really does. But it only solves a problem that where the quantum computers don't have exponential speed up, I think, and it also only does this with a big error rate and so on. So so to answer the question in a different way, Barry, there is no proof of quantum supremacy yet. So quantum supremacy means that you have a real quantum computer that solves a real world problem with the same exacting as a classical computer, much faster, exponentially much faster, not exponentially. So in theory, the quantum computer has exponential speed, as we saw here, right, with the Deutsch-Rosa algorithm. But in practice, it's not exponential, and we will now see why. And that's because of the things that you mentioned, the physical problems. So the problem, if you go out in the cold, just in your underpants, and it's snowing, you will quickly freeze. And the reason that the heat of your body is by entropy is distributing around you, right? And so this is called the second law of thermodynamics. And so these thermodynamics problems lead to two fundamental problems with quantum computing. The first one is relaxation, and the other one is decoherence. Relaxation means that a system left to its own tends to enter into a thermodynamic equilibrium with its environment. So like if I lay down in the snow after the sauna, at first it feels good, but very soon my body will be as cold as the snow, and then I will be dead. And so this is thermodynamic equilibrium. On the other hand, if I go into the desert with 40 degrees in the shade, my body will remain in 37 degrees. My surface of the body will be hotter, but my circulation my organism will work to get rid of the heat by sweating and so on. But when I cannot sweat anymore because there's no liquid anymore left to sweat, I will become unconscious, and then another 2 hours later, I will be dead, and my entire body will have the temperature of the sand in which I'm lying. And this is relaxation. And the relaxation time T1 is the characteristic time in which a system exponentially reaches its stationary state. The human body takes a bit longer because as long as it has energy, it can fight the environmental difference, but when the energy is gone, it can't anymore. Decoherence is the loss of the superposition state of a quantum system. That's not a classical effect. Relaxation is a classical effect. There's relaxation everywhere. But decoherence is the loss of the superposition state of the quantum system. So because it interacts with the environment, it is energy exchange. Any superposition state C0 of time state 0 plus C1 times state 1 with C1 element complex numbers, and the square of them equals 1. The sum of the squares equals 1. The qubit reaches the base state 0 or 1. Then the qubit merely behaves like a classical bit. So because the superposition is what makes the quantum computer efficient. And so the decoherence time is usually exponential as well. And usually it is much shorter than the relaxation time. So what is really the problem is decoherence. And decoherence takes, and so we also have decoherence on classical computers, which software engineers or computer hardware engineers call bit flip. So that can happen on your hard disk. That's why you can have data, corrupted, like the file that said, where Microsoft said, I want to repair this file, that probably where the file is stored on the hard disk, bit flips occurred, and some of them must have occurred in the metadata. So the file has metadata at the beginning, and there must have been bit flips there. So if Microsoft PowerPoint tries to open it, it will check first for the syntactic validity of the metadata. If the metadata is syntactically valid because the curly brace isn't closed or some other, then it will say the file is damaged. And that's what happening. That happens due to bit flips on the hard disk. And bit flips on the hard disk are bad because they also get copied onto the backup disk. And so that's relaxation, but decoherence is much worse because decoherence doesn't happen, of course, on classical computers because it's a superposition phenomenon. And because the time, so decoherence time for today's quantum computer is 1 millisecond. So you create a quantum superposition state, and after 1 millisecond, it's gone. So you need to finish all your computations in less than a millisecond. Otherwise, you lose the advantage of the quantum computer. That's pretty bad. Now, these thermodynamic phenomena are exponentially proportional to time. They're very, I mean, their likelihood increases exponentially with time, and they lead to errors. And the error rates are typically proportional to the rate of operating time, to decoherence time. Hence, any operation must be completed much more quickly than the decoherence time. As described in the threshold theorem, if the error rate is small enough, it is thought to be possible to use quantum error correction to suppress errors in decoherence. This allows the total calculation time to be longer than the decoherence time if the error correction scheme can correct errors faster than decoherence introduces them. So if I have a decoherence time of 1 millisecond and I have an error correction that operates in a tenth of a millisecond, then I can actually beat the decoherence and keep the computer stable. But it seems that I need a greatly increased number of bits. So what I have then is that I have now one, what they call logical qubit. Logical qubit, and this logical qubit is made up of X physical qubits, and this X seems to be so if I have, it seems to be between L and L square, where L is the number of digits and the number to be factored. So now let's say so this is a Shor algorithm. So the Shor algorithm is an algorithm that is sorry. Yeah. So that means that it's if I have L digits in the number to be factored, then I have I need to have. Sorry, I need to understand this once more. Yeah, so if I have, for example, 10 digits in a number to be factored, I need 10 or between 10 and 100 qubits. And the error correction algorithms would inflate this figure by an additional factor of L. So for a 1000-bit number, this implies a need for about 10 to the 4 bits without error correction. With error correction, it's 10 to the 7 bits. So that's 10 million bits for a 1000-bit number. And 1000-bit numbers are not so unusual. And so 10 to the 7 bits, 10 million bits, I would need to run the Shor algorithm on a 1000-bit number successfully, because I need 1,000 times as many bits for create one. So for one qubit, I need 1,000, at least 1,000 physical bits. So if I want to have a 1,000 qubit computer, I need 1 million physical bits. And so the 1,000 qubit number is a number that is by the quantum computer science community regarded as the minimum number of logical bits to do anything with for a quantum computer. So I need 1,000 logical qubits, which means I need 1 million physical bits. And this is daunting, because each of them has an infinite continuous variable because of the complex number in front with the Bloch sphere, you remember. And so each of these, and I'm not going to talk about how error correction works today, but it needs a huge overhead, as you've seen, at least a factor of 1,000. Some people believe it's even 10,000 or more of bits that I need for a qubit. So this error correction has already been done experimentally a couple of years ago. So they exist for single qubits. There already exist successful examples of how to do it, but not at all for that many bits.
You want to have a break?
Yes, we could have a small break, but you have a question before.
Yes. So do you mean that in order to like this error correction process, this is done by having these 1,000 of physical bits to support one?
Yes, they get combined in a clever way to emulate the logical bit.
So in order to run one logical bit without error, you need these thousands.
Or 10,000 others. Yes. Yes.
Process.
Yes. So that's just insane, a huge number, right? And yes, your question.
Yeah, so I want to ask, so if I understood correctly, the moral of the story is that not only is in some sense very hard to put quantum computer into good use today, but it will be very hard to do it in the future. Also.
Yes. So that's, I will get to this point at the end, but before that, after the break, I will talk a bit about the types of algorithms for which quantum computers are useful, which is even restrict their usage more. Because, for example, for machine learning, there are no applications where machine learning is better, where there's a speed up, because for machine learning algorithms, there's no way to put all the information that occurs into one bit that I can measure. I always need to be able to put the information into one or many less bits than I have to have in the other computing, in the classical computing, and that's the big problem that there are among all the problems that I can put into an algorithm. There are not so many algorithms which are amenable to the quantum speed up. And then one more thing before the break. So if you think there are many quantum algorithms that achieve a polynomial speed up, like I showed yesterday, n in a normal computer and square root of n in a quantum computer. So for example, the normal computer uses 100 operations, the quantum computer 10. The normal computer uses 10,000 operations, the quantum computer only 100. That looks impressive, right? That looks quite impressive. But if you think that we need 1,000 times as many bits, to do the error correction, then all the advantages of the polynomial speedups get eaten up. And so basically, we can only those, in theory, only algorithms that allow exponential speedup, which is this, right? So you have two n here and n here. So this is, for example, I think I put this yesterday. If I have 5, that's 32, and here I only need 5. But if I have 10, so that's 8 and 256, 9, and yeah, so that's 1024. Then I have 10 here, and if I have, to make it more impressive, 12, which is 4,096 operations, I have only 12 operations here. Right, so that's an exponential speed up. And only very few problems lead to an exponential speed up. And only they can basically, but even here, if you think about that you need so many more qubits, you need quite a high n, like something like, 2 exponent 30 or something, so that you get, in theory, you then have 30. So that's a very huge number. And so then only if you have such computations, you get the advantage, but then you need a huge number of qubits.
Yeah.
So this is really a big problem in quantum computing, and this is why the whole hype around them is a bit, hysterical. So a quantum computer, from the theory of computing, what's very important, we saw that we are in the circuit we looked at here, we are just multiplying those matrices, right? We multiply the U matrix with the H matrix 2 times, then again we multiply with the H matrix. So we just do multiplications, and I wanted to highlight here once more. So if you apply the Hadamard transformation to this gives you a 0, and this gives you a 1. Look at this again, because I showed you the Hadamard transformation here. So the Hadamard transformation, it's now overwritten, but here was the Hadamard transformation of 0, 1, and on 1, 0. The one gives 1, 1, the other one is 1 minus 1. And here you see this one. This one will give you, if you Hadamard transform this, it will give you 0, and if you Hadamard transform this, it will give you 1. So now going to the quantum computability. So the set of problems that can be computed with a quantum computer is the same than with a conventional computer. The Church-Turing thesis is also valid for them. So that's important. So it's not that quantum computers could be hypercomputers. A hypercomputer would be a computer that could solve problems that Church-Turing computers cannot solve. Now the quantum computer. Now I think that it is, it has been proven that there can be no hypercomputers, because hypercomputers would have to be able to process infinitely long numbers as input. And so this is an important argument by Martin, David Martin, what's his name? We cite him in the book, who showed that hypercomputation is impossible. He proved it mathematically, because you need infinitely long numbers to build a hypercomputer.
Martin David.
Martin David, or David Martin, yes. And I think Martin David is the name, yes. And Martin Davis. And in theory, they can solve some problems much faster. But the classical computer can simulate any quantum computer because the effect of the gates on the quantum register corresponds to a matrix vector multiplication, right? So you have a big matrix, you multiply it with a vector, you get the result. So the classical computer merely must compute all these multiplications to achieve the start-end state of the register. All problems that the quantum computer can solve are also solved by a classical computer and vice versa. So you can also use a quantum computer to simulate any classical computer, which is a bit more difficult because remember the logic gates of the classical computer, many are non-reversible. So you need to reformulate them as reversible gates. There's a gate called the Toffoli gate that can be used to model the classical operations of the classical computer as a reversible unitary matrix multiplication. So quantum supremacy would mean that there are problems which the quantum computer can solve so much faster than a conventional computer, that a conventional computer cannot realistically do it in a useful interval. So far, it has been not demonstrated because the quantum computers we have don't have enough logical qubits to do that, right? So David DiVincenzo came up with criteria of scalable quantum computers. So the first is a scalable system of well-characterized qubits. That's a register. All qubits can be brought into a well-defined initial state, which is usually that they're all in zero. This already is never fulfillable in the physical world because they will never be exactly at zero. The universe is set, which already is an error source in itself, because if you have many bits that are not exactly in zero and you start computing on them, then you can introduce errors, right? Even without relaxation. The universal set of quantum gates can be executed. Single qubits can be read out. The relevant decoherence time is much longer than the time to realize an elementary quantum gate. So that you get kind of, because the decoherence time, and so that there is an adequate error correction, the error rate per gate is below the defined threshold, and the networking conditions for larger computers, there exists a quantum interface between stationary and mobile qubits. And mobile qubits can be exchanged reliably between different places. This is also quite difficult because you also have decoherence when you exchange the qubits. We don't have, as I explained to you yesterday, quantum repeaters. So the network can only be a local network of quantum computers because if they are more than 150 miles apart, you have quantum decoherence and so on. So these conditions 6A and B are also really hard to meet.
So can you explain what a mobile qubit is?
Yeah, a qubit that is sent that is not in its ion trap, but that's sent over the wire. And so for normal computers, that's trivial. You have just the cable like this one. Electrons are encoded in a certain way. They go through, they go in here, and then they go there, and they are retransformed into pictures. And so this is for classical computers easy. It's just electricity coded in a clever way. But for quantum computer, this is already totally infeasible, right? So just transporting them from one computer to the other is very challenging.
So before you go on, can you tell me what is the input of a classical computer is a binary vector?
Yes.
And the output is a binary vector or a flat.
Yeah.
What is the input of a quantum computer?
Yeah, also zeros and ones. I mean, usually the input is the state how you set the register. So you give the quantum computer, for example, you want to factorize a large number. So you give the quantum computer this large number and code it in binary digits. And then you give these, and then you have to initialize all the register to show this number. And then you run the factoring algorithm, and then it will run and run, and then you only need to measure a few of the quantum states of the single qubits to determine the factors of the quantum number. And so the algorithm shows them in a compressed way. And you don't need to measure, you don't need to do what you do with a classical computer, which is really tedious. But if you look at the factorization algorithm written as a matrix multiplication, then you can see, of course, how you could implement it in a classical computer. But it would just run for forever, or not forever, but many years to compute, even on a very large computer. Because it's such a big matrix multiplication where so many additions and so on have to be made. So now this is Mikhail Dyakonov, a Russian physicist working at the Montpellier CNRS since many decades. He is quite famous. I think he's doing experimental physics. Yes, he's an experimental physicist, and he's quite famous. He has many great achievements. Now he's over 80. So he writes in his nice article, The Case Against Quantum Computing, the state of the classical computer at the start of any given clock cycle can therefore be described by a long sequence of bits corresponding physically to the states of individual transistors. With n transistors, there are n2 exponent n possible states of the computer to be in. The state of a quantum computer with n qubits is described by the values of 2 exponent n quantum amplitudes, which are continuous parameters, which I showed you many times in this talk, that there's this complex number c in front of the state, and that therefore you have infinitely many, I show it again once more, on the Bloch sphere here. This equation shows you that there are infinitely many, because you can, theta, if you put all the combinations of theta and phi in there, that exist, there are infinitely many, and you get infinitely many numbers on the sphere. And because of this, each qubit is an amplitude with a continuous parameter. Experts estimate that the number of qubits needed for a useful quantum computer, one that could compete with your laptop in solving certain kinds of interesting problems, is between 1,000 and 100,000. So at least 1,000, but for many problems that I can solve with my laptop computer, I need 100,000 qubits. So the number of continuous parameters describing the state of such a useful quantum computer at any given moment must be at least 2 exponent 1,000, which is, say, about 10 exponent 300. A useful quantum computer needs to process a set of continuous parameters that is larger than the number of subatomic particles in the observable universe, because there are less than 10 exponent 300 of particles in the observable universe. And with observable universe, it means not only the Milky Way, but all the galaxies that are observable with the Hubble Space Telescope, which are many. And all of them together, with all the millions of stars, billions of stars, and all the planets around them, contain less particles than a quantum computer that needs to process as continuous variables. And here's also a book, Will We Ever Have a Quantum Computer? Which I haven't read yet, but I've ordered. I look very much forward to reading it. It should arrive next week. But quantum computers are error prone. In theory, once we correct the error per qubit per quantum gate below a certain value, indefinitely long quantum computation becomes possible at a cost of substantially increasing the number of qubits. Those extra qubits could handle errors by forming logical qubits using multiple physical qubits. I told you this. How many physical qubits would be required for each logical qubit? No one really knows. That's still the case. But estimates typically range from about 1,000 to 100,000. So the upshot is that a useful quantum computer now needs 1 million or more qubits. No one has yet figured out how to combine many physical qubits into a smaller number of logical qubits so that can compute something useful. So yes, it has been done for single qubits, but not for many. In the physical world, continuous quantities, be they voltages or the parameters defining quantum mechanical wave functions, can be neither measured nor manipulated exactly. This now speaks the experimental physicist. That is, no continuously variable quantity can be made to have an exact value, including 0. Could we ever, and he writes in his text, though this is hard for mathematicians to believe, I know that it is like this because I do these kind of experiments every day. I've never been able to cool everything to 0 Kelvin. So it's quite funny how he describes it. Could we ever learn to control the more than 10 to 3 exponent 300 continuously variable parameters defining a quantum state of such a system? My answer is simple, no, never. And because the system, you have to see that if you have 1,000 values per qubit computer, you have this very enormous wave made of 1,000 single qubits, which has then 10 exponent 2,000 state combinations, each of which are continuous, and it has, but in reality it will be much, much more because it will be rather 10 to exponent 1 million. If you have 1,000 physical qubits for each logical qubits. But of course, the physical qubits all need to be controlled as well to correctly make up the logical qubit. So he believes there will never be useful quantum computers. Rolf Landauer, a German Jewish physicist who had to flee as a child to the United States, is very famous. He invented the Landauer principle, which says that the deletion of one bit of information leads to the production of at least heat W where Kb is the Boltzmann constant and T the surrounding temperature. So you have constant, the Boltzmann constant is very small, but still the Boltzmann constant multiplied by the constant temperature expressed in Kelvin multiplied by logarithm of 2 is the energy that that you need to delete a bit of information. And so this slogan's information is physical. And so he showed that not only the production, but also the deletion of information needs energy. And he wrote that theoretical publications about quantum computers should include this phrase. This scheme, like all other schemes for quantum computation, relies on speculative technology, does not in its current form take into account all possible sources of noise, unreliability, and manufacturing error, and probably will not work. So he was also very skeptical about quantum computers and their feasibility because of the quantum decoherence. And I'm even more skeptical, but I will say this to you in a minute. Do you have questions concerning the reasoning of Dyakonov or Landauer? And I think it's interesting that they are both Europeans. I think they are arguing, so I think there's a very, very big difference between Western thought and Middle European thought. You can see this especially if you read Dostoevsky or Tolstoy. You see that Middle European thought is or Eastern European thought is very different from West European thought. And Germany is in between, right? But Germany is not, now Germany is totally part of the West, but Germany traditionally, until the time when Germany still was a productive country, I mean, in the time of doing productive philosophy and science, and the leading country, it was not part of the West. You can see this if you read Heidegger. Heidegger is certainly in many ways his thinking is not Western at all. And I think calling continental is wrong as well because he's not French at all. And so it's really, and so these are two continentals, and it's typical of these continentals to be skeptics. But just as a side note. So
there is a movement which is based in Brazil and Portugal, which is called transatlanticism.
Yeah.
And for the transatlanticism, France is already part of Eastern Europe.
Yeah, though I think that's wrong. So I think if you look at Cartesianism, very Western, right? And so what are the main ingredients of Western thought is British, I call it British now because I don't want to make these mistakes with English versus Scottish. But basically, it's British positivism and tabula rasa philosophy, and French statistics. That's really Western thought, Western modern thought. And Germany, I mean, in Germany, this was rejected. And even though Kant was a diehard Aufklärer, Enlightenment philosopher, he rejected this as well. And so this is really a big contrast. But anyhow, that's a side remark. Any other question on this?
On the distinction between Western
and Middle European, yeah.
That's why you don't the traditional Western Europe.
It's not traditional. It only became that in World War II. Before that, Germany, the most of German heavyweight thinking was done in the east of Germany, Königsberg and in Saxonia. And there was another cultural center, of course, in close to Stuttgart, which is more west. But basically, Göttingen, Marburg. But all of this is totally. If you read the text, they totally reject. They were really totally vehemently against the French and the English philosophical tradition. There was a huge rift, and you can not only see it in philosophy, but you can see it also very, very strongly in literature. If you read, let's take Robert Musil. He's really Central European cultural philosophy. It's really very different from Western thought. You know? See, there's a big difference, and when I was younger, I didn't realize this because already in the 80s and 90s, when I grew up, philosophically, so to speak, West Germany was thoroughly Westernized, you know. But more traditionally, it wasn't, and so that's not by chance that many of the skeptics come from Europe, and so these two are really great. Now,
I would like to ask a question about the AI people. That would be interesting to know what is being taught in Subsidiologia about quantum computing.
So let's first do the philosophical conclusions. So I think that quantum mechanics does not give us an understanding of nature. It merely gives us some laws that we can exploit for engineering. These laws are based on mathematical entities that we use as analogies for what we measure in quantum experiments. So when we build something like the Stern-Gerlach apparatus or an MRI, we measure something that's going on in nature, but I think it's only part of what's going on in nature because our machines that we use to measure the phenomena automatically confine what we can see, right? We can't, it's not like in classical physics where we can observe with our eye what's going on, but we need to build very sophisticated machines. I think they only give us a partial impression of what's going on. But from this partial observation of nature, it's a bit like the Platonic cave. Yeah, and from these shadows that we see on the wall, we now construct our theory, and we use mathematics to do it, and now we have laws, and these laws are used to make new machines. But the new machines are basically based only on what we measure with the other machines, like the MRI, the laser. These are just machines based on these partial laws. Despite this limitation, quantum, and so if you look at the helium molecule or the hydrogen molecule, it seems that what we can measure with the Stern-Gerlach apparatus, and from which we then can derive the Schrödinger equation, is sufficient to describe quite a lot of properties of this atom. So it's not an incomplete, it's not totally incomplete, so it's really useful, even to describe natural, but it breaks down with more complicated structures, and I think that's because it's incomplete. And so Einstein was right when he said that quantum mechanics is incomplete. But he didn't see that it's incomplete because its observations are incomplete. Despite this limitation, quantum computing is one attempt to use these laws to improve computation. Quantum computing is hampered by the instability of qubits and the breakdown of the wave function upon measurement. So the former makes polynomial speed up from n to square root of n or better, but not exponential, totally useless because the gains are eaten up by quantum error correction. I've told you this already. For problems with exponential speed up, there are no physically available computers yet because the error correction is too expensive in terms of qubits. Some believe they will never come. So this I mean with breakdown of the wave function, because the breakdown of the wave function can only be utilized properly if the wave function is properly parametrized, right? And so now I have a wave function that happens in many qubits, very complicated wave function. Now I measure it in one or several qubits, but I have to rely on that the measurement, that the wave function behaves deterministically in the way I want, and this I cannot guarantee. The quantum computers would only achieve supremacy for selected problems with a structure which enables the use of entanglement and qubit readout. So that's the point. So we saw this algorithm by Deutsch, which enables, which utilizes entanglement and de-entanglement. And after the de-entanglement, you can get the result in exactly one qubit. And why is it, by the way, exact? Because it assumes that you have set it to the exactly right value at the beginning. And then because the transformations done by the unitary matrices are deterministic, you can rely on that after retransforming it back into with a Hadamard gate, you can measure it. But this entanglement, but there are only very, very few problems for which exponential speed ups are available, and very few are known. And the list that Barry just read me, a list of the many applications of quantum computers, but all of them assume that for many problems it is possible to actually utilize the speed up. But that's not the case. If you read, I just read a very new, it's called How Much Structure is Needed for Quantum Speed Up by Aronson. He's quite a genius in this area of quantum computer science. So he has developed many very sobering theoretical results, mainly about, which are very interesting, mainly about that whenever somebody comes up with a quantum algorithm that is polynomially faster than a classical algorithm, he has shown several times that there are on the classical computer better algorithms which even eat up again the polynomial speed up of the quantum computer. So very often the quantum computer people look for algorithms that are not efficient in this classical computer space and then design quantum computer algorithms that are polynomially faster. Then the classical computer people say, well, this algorithm was designed in the 50s. Now we have so much more experience, we haven't touched it again, but let's think about it again. And then they find a much better way to do it on the classical computer.
And when the quantum people work in the way that you just described, do they just create models?
Only models. That's why Landauer, this scheme, like all other schemes for quantum computation, relies on speculative technology, does not in its current form take into, and so on. It's just true for almost every paper that appears in quantum computing still. And he said this in 1986. I love these kind of people, you know, it's just great. So this is what I mean with Central European thought. And because the Americans, in the American, my grandfather Landgrebe used to say that English philosophy is a Händler philosophy, which was created by people of traders. Yeah. I think it's a bit tough, but there is something to it. And so this skepticism brought against it. I just love it. So so this will not enable supercomputation and will not improve. And so I think that quantum computers are unlikely to radically change our understanding of nature. Even if we could build quantum simulators, one of you asked for quantum simulators. And I think that's the reason it's the following. If we are able to build quantum simulators that can, so let's take the lithium atom, which has 3 protons and 3 electrons. We can't write a Schrödinger equation model of it. There's no
Lithium.
Lithium. Yes. But if we could build a quantum simulator that could in a way natively simulate using qubits the behavior of the lithium atom, we could maybe create a simulation of it and of its states, how it moves between the states in the quantum computer. I'm certain that we could do that, though I haven't read this literature. So for the next course I give in November, I will read literature about this because I find it very interesting what you can do with these quantum simulators. But the problem is still because they will be very restricted in the terms of number of logical qubits they can provide. They can only again model small systems, So, but it's certainly clear that if you think of a system with 16 particles and you have 16 qubits, logical qubits, so you need 16,000 real qubits, and now you have basically an amplitude in there, Schrödinger wave in there, where then you can just run it. And so at some point you can do measurements, but you don't have to calculate anything anymore because it happens physically, right? So it's a cool idea, but I don't think it will lead to the simulation of the binding of the full simulation of the binding of a ligand to a protein, because there are thousands and thousands of interactions that are happening which you can't get into the quantum computer. So I think quantum computers are totally overestimated. The hype cycle will end after decades of unfulfilled promises. So this is usually the case when things are promised that are not delivered upon, then the hype cycle ends. And one important example is what's the name of this in English? Brennstoffzelle. You know what that is, Barry? Yeah, it's yeah. Yes, fuel cell. Thank you. So the fuel cell is a machine that takes hydrogen as input and produces electricity as output. And if you think of it, one reason why I would never get such an electric car is because I don't want to wait on a trip to Lugano, spend in total, 8 hours driving plus 4 hours waiting for the car to recharge. And then I have a third of the time I spend waiting somewhere in a very boring place, So I certainly don't want to do that. And so therefore I'm not going to buy an electric car, and especially, well, that's because it makes more carbon dioxide than my diesel, but that's another thing. But basically, so it's a great idea to avoid this problem of having to stop to recharge your battery, and also the whole environmental horror of this battery, which is very, very expensive, and the mining of the metals is very polluting, and afterwards when its life cycle has ended, what do you do with it? So it's a real problem, this heavy battery. And it increases because it weighs a ton. It increases, of course, the amount of electricity that my car would use. So basically, if I had a fuel cell in there, I could just have a tank of hydrogen and refill the hydrogen like I refill the fuel now, which would, of course, be much efficient. And because of the high energy content of compressed hydrogen, I probably could do the trip from Cologne to Lugano in one go without even refueling and so on. But why isn't it coming? Because there are so many problems associated with the hydrogen itself. Because the hydrogen, it's so bad, it's so difficult to put the hydrogen, it has to be cooled or put under highest pressure to be liquid. And then, how do I safely get it into the fuel tank? And the problem is that how do I keep the fuel tank? Because the hydrogen tends to leave the tank, even if the tank is a closed system. So there are so many engineering problems around the hydrogen tank that the fuel cell hasn't made it. But I would really like to have a fuel cell driven car. But it's a form of clean energy. But and it solves this difficult problem of the battery infrastructure, and you also, if you would do it like this, you could transport the hydrogen around with lorries. And then basically, like today, they are bringing the gas to the gas station. They could bring the hydrogen, so you wouldn't have to burn the power net with the electricity. That now there's an unsolved problem. If all Europeans would drive electric cars, the power net would break down immediately because it's not made to transport such big amounts of electricity and so on. But it hasn't come around. So, and because it was promised since the 1950s, now nobody talks about the fuels anymore. You know, it's really a special thing that is getting used in some industrial applications, and that's it. And that, I think that's very interesting. And how this hype cycle ended. That's just one of the examples of many hype cycles that ended. And so I think quantum computing, I don't think that I will witness. I have another 30 to 35 years to live. I don't think if all goes well and I don't get cancer too early, if all goes well, you know, and if this is true, then I will not witness this, that we will have quantum supremacy, because I don't believe that we will be able to build a reliable quantum computer with 1,000 logical qubits before I die, and maybe never. And never is what this guy says, you know. Diakonov says, I don't know whether he's right, because I'm very reluctant to say never. I only say it for artificial intelligence. There I'm very certain that it will never occur, but for quantum computers, they still may be possible due to unforeseen evolutions. But the deep reason I see they're not possible is that we don't understand the quantum world. We really don't understand it. We have only a kind of superficial knowledge of it, which allows us to do some very, very beautiful technology like the MRI. So impressive, you know, that you can make 3D pictures just with a magnetic field. You can make 3D pictures of the brain. It's incredible, you know. But it's only very limited. I think that's the ultimate reason why we can't do it. So that's what I wanted to tell you in this part of the course.
So you should explain that when you say artificial intelligence, generally.
Yeah. Well, what they call artificial intelligence without the general is just a specialized algorithm anyhow. So that's possible, of course, but that has nothing to do with intelligence that is like animal or human intelligence. So we have beaten the clock. So if you want, we can do another 20 minutes going back to artificial intelligence, or we can stop for today. Or do you have any questions, first of all?
Why you mentioned that even if we can get a useful quantum computer, they wouldn't be very useful for the type of computation that artificial intelligence requires. Why is this?
Because for matrix, so the most frequent operation in artificial intelligence is matrix multiplication, matrix multiplication, but not of matrices like the ones we saw here, like quantum gates, but just classical mathematical matrices. And for this, graphical processing units are very efficient, and so quantum computers can only get a very, very minor speed up, even not square root, but I think it's like divided by 2. And then you need, for example, if you think of this neural network that is trained for ChatGPT, you need millions of qubits.
Yeah.
I mean, so you need so many qubits, or 10,000 of qubits. So you need many, many qubits. Plus you need the speed up is so little. So if you would say we need 100,000 qubits to do that, I don't know how many, and we need 1,000 times more physical qubits for this 100,000, then you already at 100 million qubits. You know, it's just and then you want to have one wave function in these 100 million qubits that you manipulate. I think that this Russian is probably right. You know, I mean, I like the Russians anyhow, not their war that they're doing now, but the Russians, they are just clever. You know, the Russian mathematics is always, there's so many great contributions to mathematics and physics from Russia. And but anyhow, that's just a side argument. But so that's the reason that there are only very small polynomial speed ups theoretically possible for machine learning. And so therefore they are not useful for machine. The only application where they are really, really good at, there are 2 big applications where they would be good if they would be big enough. The one is factoring. The other one is something with logarithmic number. I don't know the applications by heart.
You mean prime factoring?
Yeah, prime factor decomposition of large numbers. And it's something with logarithms, but I don't remember. And the third, then there is, and that can be used for cryptography. So you could, as I said yesterday, you could decipher private key encrypted message without knowing the private key. So if you had a very big quantum computer, and this you could never do in useful time as a normal computer. And then there is the search of the needle in the haystack, but I don't think that it's very easy to obtain supremacy there, because it's also only polynomial speed up. And whenever there's only polynomial speed up, I think that it's not, as far as I can remember, then it's not very, then you can't use a quantum computer for the technical reasons we just discussed. I mean, it's interesting if you think of quantum decoherence. So you could ask, but why is nature stable if there's quantum decoherence? Now, the decoherence we are talking about here results from an artificially made entanglement, right? So what a Hadamard gate does is that it artificially entangles the two or more qubits with each other. So that's not what you have naturally. I mean, there are certainly natural phenomena that lead to entanglement, but they play no role for the macroscopic stability of our world. So basically, the quantum phenomena all can be aggregated to classical phenomena, of course, if you have bigger entities, and then you don't have the quantum effects anymore. So they only occur at these very small scales, and they aggregate to classical phenomena. So the macroscopic world is classic, behaves in a classical way. That's, by the way, why we also have such big problems in quantum field theory, because quantum field theory is based on measurements of quantum particles in macroscopic contexts. Maybe that's something to show you at the end. Should I show this, Barry? Yeah. I think that's probably a very informative slide. So where is this nicely explained? So for example, when you have a particle trajectory, right, in an accelerator, so then in particle physics, you are using accelerators of the classical Lorentz force. But from a quantum mechanics perspective, we cannot measure classical principal particle trajectories. And so at high resolution, it becomes clear that the trajectories are a series of separate measurement points, which is an essential result following from the underdetermination of the quantum physics with regard to location and momentum. So because of the Heisenberg uncertainty principle, when we measure trajectory, we can only measure points on the trajectory. And so what we really measure in the detectors are subatomic scattering events, but we don't measure real trajectories, right? And so if we now go and look what that means for quantum field theory, so then we don't have particles anymore, but we only have field quanta, and they are really not determined really well. And I can't go into this all right now, but it's very, very shaky. So quantum field theory has virtual particles to make its equation valid, and then it had quasi-particles and so on. So basically, because of this inability to use macroscopic measurements to really measure the quantum world, because there's always a classical physics apparatus between us and the quantum world, we get into a lot of trouble in physics. And so I can't explain all of this now because it's another course. But I think that
I would like to say something.
Yeah.
So my understanding of the consistent histories of the interpretation of quantum physics is that given any, let me try and get this correct, given any physical state, and I'm being ambiguous now about what state means, we can understand it in classical terms, but we have to understand that the classical description of the state is only one probability in a whole set of probabilities. We don't know. So the quantum state is essentially probabilistic.
Yeah, but that's also what Niels Bohr says. For this, you don't need consistency.
Okay, but
yeah.
And so what you say here may be an exaggeration.
What?
Well, QM cannot explain a single measurement. QM does explain a single measurement by saying it's a probability.
Yes, but explanation is not probabilistic.
If
So
something is
explain,
probabilistic,
nah,
explaining it.
that's a prediction. But explanation means that I can, here I mean explain in the sense of being able to determine a non-probabilistic causality.
Okay, then
This
that
is
can
how-
be, when we rise to the level of coarse grained rather than fine grained.
Then we can do it.
And we can give it explanation.
Yes.
And
But-
so quantum physics doesn't undermine classical physics.
No, I'm not saying this. This is not, and the whole consistent history theory is only talking about quantum mechanics. What, in the sense of the Schrödinger and the Dirac equation. What this is about the problems that arise if you add quantum, quantum field theory and group theory, and then you get totally group theory. Then you get completely contradictory views of what a particle is. So that modern physics. So if you ask a physicist, the modern physicist, what is a particle? We say, oh, in the operational sense is this, in the classical quantum mechanical sense is this, in the classical physics is this, in group theory is this, in the quantum field theory there is no particle anymore. So so this shows you that we are really at the limit of what we can achieve as human beings when you look at the quantum world, and therefore it's quite daunting to build a quantum computer. And I think you know, if you the hopes that are put into quantum computing, this hype has also almost a religious character, but it's not very rational. And I think what this Russian guy here does is just put a very rational and sober point of view against it and says, well, you know, can we really control so many continuous variables in one machine? And I think it may not be possible to do that in the same way that we can now not say what is really a particle. So there the results that today's physics cannot give us a clear understanding of what particles are. The world must be made of something, but we cannot see it. Yeah, so in a way, we are back to Democritus, because classical physics, I mean, the most advanced theory of matter doesn't have a particle anymore. That's really tough, isn't it? So that the quantum field theory is really a very, very beautiful theory, but it has a lot of places where it needs to have entities that are written into mathematical equations that shouldn't be there to begin with, because they're mathematically impossible, so that it can be held together mathematically, and it has given up the notion of a particle altogether. And I think this shows you also a bit. I think it's not only an intuition, but this illustrates how can we control a machine of which we don't really know how it works, because we cannot imagine the state of the multidimensional Schrödinger equation wave in the big quantum register. We just can't.
Well, we would have then
A measurement.
certified quantum AI. In other words, we would have to test
Yeah.
multiple runs through the.
That's of course an approach also. Basically, I think that's one of the approaches to get logical qubit, right? But the problem is still that if this would give, and today if you read a practical quantum computing paper, you always get an error rate, like 3 or 4% error. And of course, then the error rate of a physical computer, of a classical computer, is 1,000,000 times smaller, right? And so the error rates are just unacceptable, but they come from the problem that it's so hard to control, even in a 50-qubit computer, to control what's going on, and so that you get such a enormous. This is an error rate that's completely unacceptable. You know.
Now, what about
If you would think that of car drivers driving with a 3% error rate, there would be no car driving anymore, because there would be crashed cars everywhere in Lugano and on all the highways